ரெக்கார்ட் பண்ணி ஆப்ல போடுவோம். வேணும்னா பார்த்துக்கலாம்.
Good evening, students. Am I audible?
Yes, sir.
Yes, sir.
Okay, we'll get started. So yesterday we completed the 5th chapter, right? That is laws of motion. So today we'll be starting the 6th chapter, which is also equally important. You know, the 5th and 6th chapter put together is for 12 marks, okay, for your term 1. We'll get started with it. Is there any other doubt from yesterday's, from the previous chapter that you guys had? Can I take it as no?
Yes, sir. No doubts.
Okay. So now it is your turn to practice. So I hope everyone has collected the study materials, right? There is
Yes.
someone who has not collected, please do it, because that will help you with all the notes, and it has all the problems, also NCERT solutions. Everything is available. So ensure you do it. Okay. So the next topic that we are going to see is work, energy, and power. That is chapter number 6. So I hope you guys know the term 1 syllabus, right? This chapter 6, you have the 7th chapter, that is rotational mechanics, and 8th chapter, which is gravitation, right? So these two are pending. Don't worry, there is a small chapter only. We'll be able to complete it. 7th alone will take some time. It's a very big chapter. So I hope you are good to go, right? So write down the heading in your notes: work, energy, and power. Right. So can you guys, so we'll start with the discussion. What do you understand by the term work?
Force into displacement.
Okay. So force into displacement is what you would have learned in your 9th standard, right? But there is a small modification to it. They would have not taught one extra term related to it because there is no trigonometry involved at that point. So generally, if you use the word work, what comes to your mind? We use all these terms in our day-to-day life, right? Work, energy, and power, right? So what comes to your mind when we say the term work?
When an external force is acted on an object or a body and it displaces a particular
And it displaces the object, right?
Yeah.
So that is according to physics. Okay, then we can directly get into the context since you guys know what it is. So we'll start with the definition itself. Work, power, and we can say WPE also, work, power, and energy. Okay, first let's look at the term work. See, generally, work doesn't have any definition of its own. It is all about if you take an object, right? So if you take an object, let's say it is of mass m, and you apply some force on an object, then what is expected out of it? So we understood from dynamics that for any object to be put into motion, the necessary thing or the quantity that is required is force, right? So when you apply force on an object, what happens to it? You can expect some amount of displacement, right? So when I say displacement, if I take the centers as the reference, then the center of this block would have got, let's say, displaced by a distance s. Okay. Now we need to observe the situation and try to give a statement to it. When a force is applied on an object, okay, and the object is, what should happen to the object? Then the object is displaced work is said to be done. Am I right? When a force is applied on an object and the object is displaced, then work is said to be done. Accepted, guys?
Yes,
Yes,
sir.
sir.
yes.
Right? But you should not accept it. The object should get displaced. Why did I leave some gap?
In the direction of force.
In the direction of force.
Yes, that is important. Then the object is displaced in the direction of force. Then we can say work is said to be done. Okay, this is more important, right? So what happens is many students I've seen, when I ask them about work done, they simply say force into displacement, but they don't have a clarity of what exactly it is. Okay. First of all, as I told you, there is no definition for work. There is only definition for work done. Okay. That is the first point to be noted. Secondly, whenever you're talking about work done in context with reference to physics, what should come to your mind is you should immediately ask a question: work done by which force? Okay. Because work done by each force keeps changing. Am I clear, guys?
Sir, in
I'll
the
explain.
sense,
I'll tell you. But have this point in your mind. Work done by which force? Okay. So have this in your mind. I'll tell you what it is. So is this point clear? When a force is applied on an object and the object is displaced in the direction of force, in the direction of application of force, work is said to be done. Okay. When that is the case, let's try to derive a mathematical expression. mass, let's say the force is applied. Am I applying a pulling force or a pushing force?
Pulling force.
So let's say yes. Let's say there is a pulling force applied at an angle theta with respect to the horizontal. Then let's say the center has got displaced by a displacement of s. Okay. Then this f can be resolved into two components. What are the two components? This component will be f cos theta, and this will be f sin theta. Now read the definition carefully. If I put a question like, what is the work done by force F? What will you say? Work done is equal to what does the definition say, guys?
Sir,
The displacement. Yes,
displacement
tell me.
into f cos theta.
Yes, it should be F cos theta into displacement,
Fs cos theta. Yes, sir.
right? Which can be written as F into S into cos theta. But we know that force is a vector quantity, displacement is a vector quantity. Right? AB cos theta can be written as A vector dot B vector, provided A and B are what? Vector quantities, right? So here F represents what? Here F represents the magnitude of force. Here S represents the magnitude of displacement. Since they both are vector quantities, the best way to write it is force vector into displacement vector, or F vector dot S vector. Okay. So this is the mathematical definition of work done by force F, which is F vector dot S vector. Please write it down. Okay. Shall I proceed? Now,
Sir,
what?
sir,
Please
I have
tell
a
me.
doubt.
Tell me.
Sir, in that block, why are we taking that center, the two centers of the block, sir, of the two blocks?
Okay. Generally, if you take the mass of any object, right? Good that you asked it. Generally, if you take, let's say there is a brick, okay. If there is a brick, imagine you're holding it with two fingers. Okay, I'll show you a demonstration. Let's forget about brick. Let's say you have a mobile phone. You have this phone, and I can hold this phone at different locations. I have two fingers. I'll be holding it. Okay, concentrate on my right hand. If I hold it like this and I remove my left hand, what do you think will happen to this phone? What is your expected result out of it?
Sir, it'll fall the other side, sir.
It will tend to rotate. It will fall like this, right?
Yes, sir.
It is falling, right? It is rotating. Okay. Now observe, if I hold it at this end, look at the rotation. It is more. I'm not able to balance it. But if I bring it closer here, it is rotating, but not as heavy as the previous one. I'm slightly able to balance. If I bring it here, the rotation is little less. Rotation in the sense with respect to horizontal, how much ever angular displacement it is making. Right? Similarly, I hold it here. Look at the direction in which it is going to revolve. Is it not exactly in the opposite direction to what was happening previously? Now,
Yes, sir.
if I hold it at this point, see what is happening. You don't trust me, you can do this activity with your mobile phone and also see. What is happening?
Center of mass, sir.
That's actually called center of gravity.
Gravity, sir.
Oh,
okay. Yeah.
Center of gravity means the point where the whole weight of this object is said to be concentrated. So this object will be made up of atoms, and all those atoms will have mass. The sum of all those mass put together is the mass of this matter, right? So the mass of any matter generally is said to be concentrated at its center. See, for example, I didn't stress on this point because I wanted to tell it later after I tell center of mass. Now, are you guys able to understand what is center of mass? So center of mass, as
Yes,
the name
sir.
suggests, center is a point. A center literally doesn't mean exactly the middle point. No. Center is a point of what? Of mass. Means if you take an object, wherever the mass of the object is said to be concentrated, that is called as center of mass. For example, if I take this water bottle, you should always hold it and see there will be one particular point where the object will not revolve. So this is a point where I'm able to see that this is balanced. So the center of mass is somewhere inside this. It's in the shape of some cylinder of varying radius of curvature, right? So it's somewhere over here. Suppose I take this pencil, I hold it here. You're able to understand? So this is the center of mass. So last chapter we learned F is equal to ma, right? Correct?
Yes, sir.
So we learned F is equal to ma. That acceleration, when I try to talk, did you guys ever think about it? This object is made up of multiple particles, right? I hope, see, I cannot show you, unfortunately, but I hope you guys can imagine using your chemistry knowledge, right? This is a matter, right? Matter is made up of small atoms, right? When this object is given a force in this direction, let's say there is a force, we wrote F is equal to mass of this object into acceleration, right? But did you ever think, why didn't we write the mass of individual particles? Why did we write the mass of the first atom, second atom, third atom, fourth atom, and acceleration of each atom put together? Why didn't we do that? What did we actually do? We took the average of all the masses. Are you guys able to understand what I'm trying to say? So when we applied this F is equal to ma, this force is acting. If I have to break it down into a smaller aspect, it is acting on all those individual particles. We never wrote it as M1 into A1, M2 into A2, M3 into A3. We wrote only one equation. What is it? Force is equal to mass into acceleration. That mass, what we were speaking there, is actually the total mass of the object. The total mass is nothing but, when you learn it in the case of center of mass, something like you will find average and all those things that you will see in the next chapter. Okay. And the acceleration which you wrote for this object is actually the acceleration of this center of mass. It is written as ACM. CM stands for center of mass. Okay. With that context in mind only, I took the center as a reference where I calculated the displacements. Because here I took a rectangle, that is why I took the exact center. If there is also a rectangular shape, I am able to find exact center as the center of mass. I hope I answered your question, right?
Understood, sir.
Everyone is clear?
Yes,
Yes,
sir.
sir.
So what is the SI unit of work done? You guys think and tell me. So work done depends on two physical quantities. What are the force, displacement, and cos theta is also there. That is a mathematical quantity. Okay. But yeah, work done will be what? Force is measured in Newton. Displacement is measured in meter. This Newton meter put together is called as joule. So since it's the name of a scientist, we write it as capital G. Okay. Now what is going to be the Cgs unit, guys? Newton
Gram
in Cgs,
centimeter.
it's
Okay.
dyne, bro.
Okay, sir.
It's dyne.
Sir, actually for kilogram meter, for that I told in
Understood.
CG, sir.
Yeah, understood. But Newton, it is directly something called as dyne. You already know this. 1 Newton is 10 power 5 dyne. And meter. Instead of meter, you write it in centimeter. So this dyne into centimeter is called as 1 joule. If you calculate and see, it will be 10 power 7 erg. Okay. So there is a relation between them. Please make a note. Tell me.
Sir, I don't get the point of Cgs units, sir. Because in the day-to-day life, we usually use joules.
But in
that kind of-
problems, the last node.
Oh,
That is one thing.
in
Not only
reality,
Cgs,
we just use the SI unit, sir.
SI unit, but sometimes erg is used in atomic level.
Oh, okay.
See, day-to-day life, honestly speaking, you never say I did these many joules of work. right?
Yes.
Have you
Yes.
ever seen the food packets? Like these days, many fitness freaks will speak about the amount of calories they consume. Is anyone of you doing it? At
Yes,
least you
sir.
would have heard about it. They speak about calories, right? So they say these many calories. That itself is wrong, because if you take the food packet and see, it will be in terms of kilocalorie. But technically, do we say kilocalorie? Illa. We say calories. When you want, you go and take Lay's packet. You take and see. No? If you will have something, biscuit packet, something you take and see, there it will be written these many calories is the amount of energy consumed. Energy is also measured. Generally, this is the unit that we use in day-to-day life. Never we say these many joules and all. Purida.
Okay,
Similarly, if
sir.
you run also, right, they say that I burned these many calories. They will not say I applied this much for these many joules. So another real time it is not applicable. But CGS unit, why we learn is sometimes for the sake of problems, and we need to have a knowledge to do a conversion, because there is a relation between joule and calorie. I don't know how many of you know this. 1 joule is 4.2 calories. Okay, wow.
Okay,
Are
sir.
you able to understand? So those things will help you. Sharia. Anything else? So 1 joule is 10 power 7. Where in dimensional formula. So what is the dimensional formula for the unit of force? Newton is written as mlt minus 2 into meter length. It is ml square t minus 2. So this is the dimensional formula for work done. And lastly, is work done a scalar or vector?
Scalar.
It's a scalar. How did you say it's a scalar quantity? Because
Sir, dot product of two.
perfect. Because you're doing dot product between two vectors. Okay. So it's a scalar quantity. So work done doesn't have any direction. So if anybody asks you how much is the work done in a particular direction, question itself is wrong. Okay. Shall I proceed?
Yes, sir.
Yes, sir.
I want to stress on one important point. Here, I wrote work done by force is equal to F vector dot S vector. No? I want you all to make a clear note. This is a formula applicable when the force is constant. Okay. There is a force. So this formula is applicable when the force is constant. So I told something called as constant. So what is the opposite of a constant? It's variable, right? Now the question is, what is the work done by variable force? So 1 minute, guys. Before I explain this, I told you this point now. Let me answer this question. I told you whenever you're asked to calculate work done, what is that? So the question that you need to ask yourself before you solve the problem is, you should ask work done by which force? If suppose they ask a question, what is the work done? Then it is wrong. The question should always have work done by gravitational force, work done by external force, work done by frictional force, something like that. If that is not there, it is wrong. Okay. So let me take the same block into consideration. Let's say this block is moving on a rough surface. So let's say you're applying a force in this direction also. Okay. So mg will act downwards, normal will act upwards. Similarly, mg will act downwards and normal will act upwards. Now, since it's a rough surface, frictional force will act in the opposite direction. So mg and mg will act across the center of mass. So I say the displacement of the object is S in this case. Okay. Now, How many forces are you able to see in this diagram?
3.
4, sir.
Capital F, N, mg, and F. Yes, 4. So when I say work done by first, capital F is what? Work done is equal to F into S into cos of, see, force and displacement both are in the same direction, right? F into S into cos of how much value? What is the angle between them? They both are parallel vectors. Cos of 0 degrees. So it will be F into S. This is the formula you learned in your 9th standard. Because there they would have not spoken about angles at all. So here, can I say it's positive work? Second, work done by, see, generally friction is represented with small f, okay? So what is the work done by friction? I'm assuming all the forces in this case are constant. So what is the work done by friction? Small f into displacement into cos of, you guys tell me. Friction is in this direction. Displacement is in this direction.
180.
Yes, cos of 180. Any idea of what is cos 180? I know you should know.
-1, sir.
Minus
Sir,
1.
no.
Correct. So it is F into S into -1. So minus Fs. Here it is.
Sir, I have a doubt, sir.
Tell me.
Sir, work done is scalar quantity, then how can it be negative?
It can be negative, huh? Negative here doesn't mean direction. Means you have a confusion in negative quantity. If I write Fs of minus I cap, then you can ask me this question. Okay. When you report this answer minus Fs, the person who's reading your paper will understand. Even before you say it is negative work, they'll understand that this force is a resistive force. Because only resistive forces do a negative work. They will try to oppose the motion. No? That is the meaning of that negative. It doesn't mean direction. Got it?
Sir?
Tell me.
Sir, so now we are seeing it with respect to the force. Sir.
Yeah. So here
So
you can
that
ask
would
me
be
what.
negative.
Yeah, negative, because we are seeing with respect to, yes, that's also right. So you're talking about friction. The work done by friction is negative because it's a resistive force. You're able to understand?
Yes,
Yes
sir.
or no? Yes. No. What is the work done by mg? That is the weight. Work done is equal to mg into displacement. But what is the angle between mg and displacement? Cos of
90.
90. What will be the answer?
0.
0.
So technically, 0 work is done by gravitational force because there is no displacement occurred according to physics. There is no displacement occurred in the object in the direction of weight. Okay. Similarly, what is going to be the work done by normal? Work done is equal to, even before I write, you should know, n into s into
0.
cos of 90 degrees. It is 0. Here also 0 work is done. So with this example, we can understand that work done can be what? Positive, negative, or 0. So when do we say work done is positive? When the force is supportive in nature. When does the work done be negative? When it is opposing or resistive in nature. When do we say it is 0? When it is a perpendicular force. Okay.
Sir, I have a doubt in the last statement.
Tell me, please.
Sir, this supportive, oppositive, and perpendicular, we cannot tell it in terms of direction, right? Sir, like
No, we
in
can't
the,
tell. You can't tell it. You can't tell it. No.
okay, sir.
This positive, negative, or 0 is only for the output result of force. Okay. If suppose somebody is saying the work done by a force is 5 joule, then what can you say? Is it a force which is supporting the motion or opposing the motion?
Supporting, sir.
It's opposed. So here you can say when work done is positive, you mean to say that the object is subjected to a force which is helping the motion of the object. Suppose somebody says work done is equal to minus 10 joule. Means you can say that this object is subjected in the sense it is acted upon by a force which is resisting the motion. Okay, if somebody comes and tells you work done is 0, then you can say that the force is perpendicular to the displacement. There are two cases, guys. It need not be perpendicular always. If work done can be 0 when it is perpendicular, or when will it be 0?
So when force is 0.
Force is 0, then you don't say no work done by a force. When force is still acting, but displacement is 0.
Displacement is 0. Okay.
You're able to understand. So displacement can be 0, or the force can be perpendicular to the displacement. Both can happen. So when will the displacement be 0? Suppose you're applying a force on this object and this force is not able to overcome the static friction. Then you can say that this force is not causing any displacement. Okay.
Oh, okay. Understood, sir.
Yes.
Sir,
Help me.
sir, for example, when we release a block from height h, sir,
Okay.
during middle of the during that activity, sir, we are measuring the work done, sir.
You have a block which you want to drop from a height, correct?
Yes, sir.
Okay. So what is the force acting on it? It is mg.
mg.
Is there any other force? I'm assuming air resistance to be. You're not taking under any air resistance or air drag. Am I right? So
Yes,
there is
sir.
it is falling purely under the influence of gravity. Okay. Now tell me your question.
Sir, so work done will be force into displacement, right, sir?
So work done, yes. What is the force acting on it? mg. And what is the displacement of it when it hits the ground? It is h. mg and h both are acting in the same direction. So cos of 0 degrees. You would have already seen there is a very famous formula.
Yes, sir. Potential.
Potential. Because in 9th standard you would have learned this definition. No, energy is the capacity to do work, but you would have not understood what is the significance of it. So here, the gravitational force, whatever work is doing, this is what is getting stored in the form of potential energy. That is why the name of this chapter is work, energy, and power. But they are all related terms. Clear? Anyways, about this we'll discuss later. I thought I'll tell it later, but since you asked, I explained it. Clear? So potential energy can also be seen as the work done by the gravitational force to displace the object through a displacement h. Right? That is mg. Right.
Sir, here downward is taken as positive.
Yes, downward is taken as positive. I'm not talking about positive or negative. I'm only seeing, whenever I calculate work, there are two kinds of handling problems. One is when you're handling problems in kinematics, right? You're dealing with complete vectors because, I understood where your question is coming from. When you, for example, the same question, I want to write it as v is equal to u plus a. Then the actual meaning is v vector is equal to u vector plus a vector into v. Here we are compelled to take what? We are compelled to assign a direction to each physical quantity, velocity and acceleration. Correct? Whereas when you solve a problem based on work done, you need not be concerned about which direction is positive and which direction is negative. You need to be only concerned about one thing. What is it? What is the direction of force? What is the direction of force? What is the direction in which displacement is acting? That's it. Okay, because cos 0 or 180 will take care of the direction. Understood?
Yes, sir.
Anyways, we'll be solving few problems. At that time, your doubts will get clear. So please give me a confirmation. Are you all clear with what is the work done by a constant force? All these things, all this formula is applicable only when the force is constant in nature. Now you can ask me what will happen when variable forces will act. So write down the heading as work done by whom? Work done by variable force. Okay. So can you imagine what is a variable force? So what do you understand if I give you a term called as variable force? What is your understanding?
Force is different from point on.
Force is different. Okay. At what context? In what context force is different? Force is different from whom?
Forces keep on changing.
That's right. So as the object is moving, you keep increasing the force or decreasing the force. So let me give you an example. Let's say there is a trolley of mass. Would have seen in these railway stations and all those things. The police will be pulling, they'll put some load on a trolley and they will keep pulling it, right? So let's say they are pulling it by holding in this direction. Okay. And they are pulling in such a way that they are pulling on a surface where there's only a scenario, guys. Don't completely get into this context. So they are pulling on a surface where this is smooth and they enter on a rough surface. A rough surface in the sense, let's say this is to be pulled on a surface where there is a little bit of sand lying, offering some amount of resistance. Okay, just a scenario. Now, what will happen? They say, let's say they are applying 5 Newton force here. When they enter this rough surface, will this 5 Newton be sufficient enough for the object to be pulled? Sometimes to make it move with the same speed. Let me put the question like this. So let's say due to this 5 Newton, this object is moving at a particular speed. To maintain the same speed, when they enter the rough surface, what are they supposed to do? Will that 5 Newton be
More
able to
force
maintain
is required
more force is required? Why?
to
Because
maintain
of
at the con.
To overcome that.
Because
frictional force increases.
the frictional force keeps increasing. Okay. Let's say the level of sand here keeps increasing. Okay. Okay, level of sand is going to increase. Then what will happen to the friction? It also keeps increasing. So what are they supposed to do during the course of the journey between B and C? They need to keep constantly increasing the force, right? So that force is going to get increased at every instant. If I try to break it into small journeys and try to observe in those small parts, because of the increase in the level of friction, they are forced to increase their external force to maintain the same speed. Now the question is, are they doing work or not?
Yes, sir.
Though they are changing the force, look at the direction. There is a component of this 5 Newton, which is phi cos theta acting the horizontal direction, and it is causing a displacement in the horizontal direction. But what is happening between the points B and C at every instant? They need to increase the value of force to make the object move with constant velocity. Now, this kind of a scenario comes. What is the amount of work done by them is the question. So my interest of study is they applied some force. Okay, if I'm able to relate that force to some mathematical equation, okay, I will try to frame a mathematical equation. And if I know the distance between these 2 points, will I be able to calculate the force will I be able to calculate the work done by this variable force is the question. Okay, so for that, what we are supposed to do is, generally, whenever you take, so we know the basic formula for work done. Work done basic formula is F into S into cos theta, but you can apply it when the force is constant, right? So the journey B to C, let's say the total displacement is S by C. Now what we need to do is, we need to break this S into small displacements of thickness ds. Generally, wherever this d comes into picture, right, we call it as infinitesimally small. What do you mean by infinitesimally small? Means you have to see that with a microscope to understand how much displacement has caused. Okay, but since I can't show it on a paper, I'm taking that distance.
Is it like negligible, sir?
It's negligible. It's small, very small. Okay, such that The integral of all this ds put together is this. The sum of integral is basically summation. I have already told you guys. So integral is nothing but sum of all these displacements put together between the points 0 and s is what is s. Okay. So have this in your mind. Generally, whenever you take an infinitesimally small value, the force acting, though it is a variable force, the force acting for that infinitesimally small value can be taken to be constant. Means, let's say I told you the force will increase from B to C, right? Let's say you have a stopwatch in your hand. They are taking 10 seconds to go from B to C. In the 10 seconds, let's say the force which they started here is 5 Newton. By the time they reached here, it is 10 Newton. Okay. And this point is there, no, this ds. Let's say the starting point of the ds occurred at 5 seconds. And between 5 seconds and 5.00000, let's say 100 zeros are there and there is a 1. Can I take it as an instantaneous value? Guys, are you able to understand what I'm saying? So whenever there is a question, what is the force at 5 seconds? Means if I measure it between 5 seconds and 5.0000, 100 zeros and a 1, I can still call it as an instantaneous value because the time difference between those two quantities is negligible. So during that time, what we can say is the force is constant. Means we are trying to calculate the force at an instant. You're not calculating the average value. Then what are we supposed to do is the small amount of work dW will be equal to F into ds. Or I can write it as F vector dot ds. Why did so this F vector dot S vector is applicable under what scenario? Only when the force is constant. So though this force is variable in nature, remember this F what I've written here is variable. Though it is variable in nature, this variable force is acting for how much time? For a time of ds, where for the time ds, this variable force can be treated as a constant. Means at every instant, the force is constant. But between 0 to 10 seconds, it is not constant. Listen to my statement carefully. Listen to the preposition carefully. I am using the word at every instant. At 5 seconds, the force value is constant. Means it will have only one. See, at one instant, you can have only one value. But between 0 and 10 seconds, you can have multiple values. So what is this? What is the work I have calculated here? I have calculated the work done by that force at a given instant where it is displaced through a distance ds. Means I took the help of this fs cos theta. Okay. Now you guys tell me how to calculate the overall work done. Wherever ds comes, it's a differential equation. So how will you overcome the differential equation? So if you have, what is the opposite of differentiation, guys? What is antiderivative?
Integration.
Integral of f vector dot ds vector from s1 to s2 is going to be the formula for work done by a variable. Okay. I'll tell you how to handle it, but write it. See, or I can write it like this also. W is equal to integral of f vector dot dx vector from x1 to x2. I'm just using a different notation. Okay. Here, guys. Now see, I've shown you how to calculate the work done by constant force. Now, suppose I give you a question like this. There is a force of 5 Newton acting on an object at an angle 60 degrees. Okay, I'll take an angle 30 degrees with the vertical. Find the work done by the force when it has caused it has caused a displacement of 5 meters. Okay, this first question. There is a force of 5x square plus 2x plus 1 is acting on an object. Find work done by the force between the points x1 is equal to 1 meter and x2 is equal to 3 meters. Let's see how you guys are solving. I'll give you 2 minutes time, solve and tell me the answer. So what is the answer for the first one?
25 root 3 by 2 joule.
25
Root 3 by 2 joule.
root 3 by 2.
Yes.
Correct. Wrong. Check it. And you didn't draw a proper diagram.
Sir, is it 12.5?
That's right. Because what is that I gave in the question?
With
30
the
degrees
vertical.
with vertical means with the horizontal, how much will it be?
Horizontal, the answer what Giridhar gave is correct.
Horizontal will be 60 degrees, correct? Huh? So
Yeah,
force
yes,
is
sir.
5.
I understood the question.
Got it? So answer will be 12.5 joule. So work done is equal to, this is an easy one, F into S into cos theta. Never forget, theta is the angle made by the force with the horizontal. So 5 into cos of 60 degrees, that will be 12.5 joule. Second one, How to do, guys? Anybody who has done it? So what is the formula? Work done is equal to, if you observe the force is not a constant value. It depends on the displacement. Right? Whenever force depends on the displacement, then work done will be integral of 5x square plus 2x, integral of f dx, no, into dx.
Yes, sir.
Dx by default you can take, x1 is 1 and x2 is 3. So integral of 5x square plus, okay. This I can write it as integral of 5x square dx plus integral of 2x dx plus integral of 1 dx from 1 to 3, 1 to 3 and 1 to 3. So 5 into, what is the integral of x square by, x square dx? It will be x cube by 3 between 1 to 3 plus 2 into integral of x dx is x square by 2 between 1 to 3. Integral of dx is x between 1 to 3. So substitute the upper limit. 5 into upper limit, that is 3 cube by 3 minus the lower limit, that will be 1 cube by 3 plus 2 into upper limit 3 square by 2 minus the lower limit 1 square by 2 plus upper limit 3 minus the lower limit 1. So that will be 5 into 3 cube is 27, 27 minus 1 is 26 divided by 3 plus 2 into 9 minus 1 by 2, that is 8 by 2. That will be 4 plus 2. So 5 into 26, the whole divided by 3 plus 4 plus 2, that is 6. The remaining part you solve. Those many units will be the answer. The reason why I wrote units is because the question, it is not given. We don't know what is the unit of force. Right? So you just take it as units and deal. I hope you understood how to deal with variable and constant forces.
Yes, sir.
Okay. Now let's look at some example from the textbook. Okay. So one more point I would like to mention is the graph between force and displacement for work done. How to calculate work done from graph between F and S. Okay. So when you take force here and displacement here, okay, I take another graph. Force here and displacement here. If I draw a graph like this, what do you understand from this graph? What do you understand from this graph sheet?
So the displacement is 0, but some force is acting.
No. Displacement is there. Force is constant. See, when I say force is constant with respect to whom? With respect to displacement, not with respect to time. Okay, here force should not be a function of displacement. Okay, whereas I take a graph like this. What do you understand? This is an example of a variable force. Okay. See, generally when you're dealing with graphs, right, there are only two parameters that you can calculate. One is slope and the other is area. Okay. Who will give us the value of slope in terms of calculus?
Differentiation.
Yes, the differentiation, and area is given by integration. Okay. And one more point to be noted is slope is generally y-axis by x-axis. Area is product of y-axis and x-axis. This is the whole. See, if you know this logic, right, you can solve any problem in physics. You'll understand when to differentiate and when to integrate also. So if a force and a displacement graph is given to us, then if I calculate force into displacement, F into S, right? If I'm doing the product of y-axis and x-axis, what does it give me? It gives me area according to mathematics, right? But according to physics, what does it give us?
Work done by the force.
Work done by the force. So whenever a force and a displacement graph is given to you and you're asked to calculate the work done, what are you supposed to do? The whole moral of the story is calculate the area under the force displacement graph gives what? Work done by the force. Okay. Similarly, here if I take something like this, where this I will call it as ds. I told you, we'll break it into small intervals. Then here work done will be what? Integral of f into ds. Okay. Generally, when I say integration, we need to take it with limits. So S1 to S2. Is the work done by the force in the case of variable values? Am I clear till this point? These are all the very, very, very important basics. Am I clear? Are the
Yes, sir.
basics clear?
Yes, sir.
Okay. So after this, things are very simple. Trust me, it is very simple that we can learn it easily. So based on this, what we will do is we'll do some more problems in the first 10 minutes of tomorrow's class. Then we'll go to the next part of this chapter, that is energy. Okay. Any other doubt, guys, from today's class?
Nothing, sir.
Nothing, right? Okay, then we can wind up. I'll see you all tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir.